Okay, in this next series of videos we're going to look at carboxylic acid derivatives. Now these are molecules that are obviously made from carboxylic acids. So carboxylic acids reacted with other compounds. Some of the important ones we're going to look at are esters, the sweet smelling ones. We'll see their naming and their reactivity. We're also going to look at making acylchlorides, which are where you've replaced the OH on the carboxylic acid with a Cl. We'll also look at their reactions as well, reactions of your acylchlorides, and finally, and also the reactions of esters. And then the green topic we will cover is making biodiesel, which is an esterification, and trans fats, which is a trans esterification. Okay, so we have 3 videos: acylchlorides, making esters, and the esters video, and then finally a green video, biodiesel and trans fats. Alright, in this video we are going to look at acylchlorides. So if we look, we also call them acid chlorides, and this is because they are incredibly reactive, and they will react very readily to and are incredibly soluble in water. And they're incredibly reactive because you have a very big carbon delta plus, and that's incredibly attractive to a range of nucleophiles. And you've also got the large chlorine delta negative. They're smelly, colourless liquids, very soluble in water because they're big dipoles. And you're also going to have hydrogen bonding, dipole-dipole, all those intermolecular forces. They're really easy to make. It's just replacing the OH group on the carboxylic acid, there's the OH group, with a chloride. And if you remember back to alcohols, we use PCl5 to do that. You remember it's a very vigorous reaction, lots of heat released. Your acyl chloride is made, you get hydrochloric acid vapour being produced, and you will also get POCl3. You will always need 1 mole of PCl5 for every OH group that you want to replace with a chloride. Okay, so it's essentially the test for the OH group, but now we can use one of the compounds that we've made when we've done that chemical test. Okay. We're going to look at how to name them. It's fairly straightforward to name acid chlorides. Essentially, if you look at the longest carbon chain, first of all, that's your stem. So count the number of carbons in your longest chain, that's your stem. So if it was just 2 carbons, it'd be ethane. Carbon number 1 is the one, just like with carboxylic acids, it's the one with the C double bond O and the Cl on it, where the acyl group, the acid chloride group is, that's carbon number 1. And so that means that all your prefixes, any branches, hydroxyl groups, any other bits that are on the molecule which are not the acyl chloride group, you need to position that relative in your naming relative to the acyl chloride carbon. Okay. So you must remember to number where they're relative to the acyl chloride. So you sometimes have to count from the right hand side back to the left. And then you replace the end, the E of ethane, so if it was ethane without the acyl chloride, with e.g. the E in ethane there, you will replace that with anyl chloride. Okay, so if there were 2 carbons in the longest chain, it would be ethanoyl chloride. The ending of your suffix is oil chloride. Alright. So we'll just have a quick quiz, see if you can name. This is also on, some of these examples are on page 1 of your notes, so you might want to fill those in now. Okay, so propanoyl chloride. I'd like you to have a go at drawing the displayed and skeletal formulae for propanoyl chloride. Also do the structural formula as well. So pause the video now, draw them in your notes. Okay. Alright, so you should have drawn them by now. The answers is, so this is our displayed formula, so C double bond O, and then we've got prop, 3 carbons in our longest carbon chain, and just fill, for the fully displayed, remember put all your bonds, 4 bonds on each carbon, with hydrogen. So the oil chloride is that latter part, the C double bond OCl, and then just draw all those. Skeletal formula, so again 3 carbons, double bond O and a Cl. And the structural formula will be H3C, CH2, I've written it H2C, CO, Cl. Cool. Alright, another one. Can you name this? That's the question. Can you name this? I've given you the displayed formula and the structural formula. Okay, so name this. Pause the video now and see if you can name this molecule. This is actually one of the examples on page 1 in your notes. Okay, so you should have looked, you should have seen that there's a big old benzene ring there, C6H5. This is given the prefix benz, and then we've got the chloride bit, so it's benzoyl chloride. So benz for the benzene, that's that hexagon there with the ring in it, which has the molecular formula C6H5, and the oil chloride takes account of the acyl chloride group that has replaced one of the hydrogens on the benzene ring. Alright, here's another one. I've drawn you out the skeletal formula this time. I'd like you to have a go at naming this, a little bit harder example. So remember, pause the video now and have a go at naming these. Alright, so you should have named the alcohol. So first thing we do is count the longest carbon chain. So it's pent. But now we've got 2, oh yeah, we've got a prefix, 3-methyl. Okay, so we've got a CH3 group coming off the 3rd carbon. And we've got 2 oil chloride groups. So we've got one on carbon number 1 and one on number 5. So it's 3-methyl pentane 1,5 di-oil chloride. Excellent, well done. Alright, so now we're going to move on to the reactions of acyl chlorides, acid chlorides. They are highly reactive. They're incredibly attractive to any nucleophile because we've got a nice planar environment and you've also got 2 electron withdrawing atoms on the carbon. Okay, so they are incredibly reactive. If you react it with water, it will readily form the carboxylic acid back again. Okay, so to reform the carboxylic acid, you just add water to the acyl chloride and you will remake the carboxylic acids. You'll also produce HCl vapor gas. So you'll see a fairly vigorous reaction with that and the carboxylic acid is remade and you'll have HCl vapor as well. Okay, so that's one that you need to learn. It's on page 2 in your notes, so fill that in. Alright, the next reaction that you need to know is the reaction with an alcohol. Okay, so reaction with an alcohol. Just pause the video. Think about this one. You're going to have the alcohol has got lone pairs on that oxygen and they are going to want to attack the carbon delta plus on your acyl chloride. So that that oxygen there on the OH is going to get right in behind the carbon, which has got the double bond O on it in the acyl chloride. So it's going to attack there. That's what's going to happen first. And you're going to reform. Essentially what you're going to make is an ester. Okay, so the alcohol has replaced the chlorine atom. It's lost one of its protons on the alcohol, and we've made an ester, and the proton's gone and joined up with the hydrogen with the chloride and formed HCl. So there's your acyl chloride. It reacts with an alcohol to make an ester and HCl vapor. You'll see there's a bit of a pattern here. We're always making HCl as our side product for all these reactions because the chloride is being replaced by another nucleophile, by another something with a lone pair that can donate in and form a bond with the carbon. Okay, alright, so that's on page 3 of your notes. The next one you need to know is the reaction with ammonia. Okay, so reaction with ammonia. Alright, so ammonia has a lone pair on nitrogen, and again it's going to want to attack from behind the carbon delta plus on the acyl chloride, and you're going to make, this may be a new compound for you, you're going to make something called a amide. Okay, so the NH2 replaces the Cl. The other proton from the ammonia has gone and joined up with the chloride, made hydrogen chloride gas. That's called an amide. That's the homologous series that the product of this reaction belongs to. It's called an amide. They're very useful amides. We can use them for polarization and such like. Okay, and then there's another one which is very similar to ammonia. So think back to water and alcohol. They're incredibly similar reactions, except instead of a hydrogen you've got an R group in alcohol. Similarly, if you react an acyl chloride with ethylamine, this is just like ammonia, except one of the hydrogens has now got an R group on it. Okay, so you've got NH2, here we go, this is methylamine I've done here. But it could be any R group. It could be ethylamine, propylamine, primary amine. Okay, primary means the nitrogen is on the end of the chain, has 2 hydrogens attached to it. A secondary one, it would be in the middle of the chain. Okay, so it has to be primary amine because you need the lone pair on the nitrogen to be able to be available and want to and attack the carbon delta plus on your acyl chloride. And remember, that's got a massive delta plus, big dipole on it, big positive dipole. Okay, and once again, so you're going to lose one of the protons from methylamine, and you're going to make a another type of amide. Okay, another type of amide. That's what they look like. And this is called N-methyl, and that would be if the longest carbon chain was 3-propanamide. Okay, so we always put the prefix. We're going to have a pre-prefix which has the R group derived from the primary amine, and the propanamide is for the longest carbon chain which was originally on your acyl chloride. Okay, so that's an amide. Again, very useful molecules in chemistry, biologically relevant. Okay, so that's all the reactions of the acyl chlorides. We're now going to just quickly look, it's a bit of extension work, the curly arrow mechanism that this happens with. Okay, that all these 3 reactions happen with. Okay. So how do these reactions happen? What's going on? What curly arrow mechanism? Okay, so they're all nucleophilic attack, and then you get, okay, so nucleophilic attack of your carbon delta plus, and elimination. Now if we add up attack and elimination, it's actually nucleophilic substitution. So here's an example. You've got your acyl chloride, big old dipoles on it, delta plus. Nucleophile goes, woohoo, I've got my lone pair, I'm going to attack that. There's a lone pair on water there, that's a nice nucleophile. Any nucleophile, any lone pair donor. So any lone pair donor, and it will attack from behind, well above the plane or below the plane, above the plane or below the plane, and we will make our intermediate, which will have, remember the double bond, carbon can't form 4 bonds, we have a negative charge on the oxygen there, and then the negative charge goes back down into the bonds, the chloride leaves, and the hydrogen from the water, the other hydrogen will reform and join that positively charged oxygen there. So you lose a hydrogen, you lose a chloride, and you get a double bond back as well. Okay. And overall, that is nucleophilic substitution. If you have nucleophilic attack followed by elimination, it adds up to substitution. Okay, good. So that's the curly arrow mechanism. You only need to look this up if you're particularly interested in how these curly arrow mechanisms occur. But it's good to understand it, because then you should be able to derive the products for any of these reactions with the acyl chlorides, and indeed with the carboxylic acids. Okay, so a quick quiz on what we've learned on acyl chlorides and their reactions. So the first question, I'm going to give you the structure of an acyl chloride. That's benzoyl chloride there, and H2O. And what is that going to make? Okay, so pause the video. Water being added to benzoyl chloride. What is that going to make? Have a think. Pause the video. Write down your answer on a scrap of paper or in your notes. Okay, you should have worked it out. We've got nucleophilic substitution. Chlorides replaced with an OH from the water, and we make benzoic acid. And our old leaving groups, the chloride and the proton, HCl leaves as well. There we go, there's some names for you just in case you need to practice those again. Benzoyl chloride, benzoic acid. Okay, well done if you got that one right. HCl vapor. Okay, the next one we're going to see is the reaction of, this is propyl chloride and ammonia. Pause the video now and see if you can work out what products we're going to make with that. So propyl chloride and ammonia, what are we going to make? Okay, so draw out your products and let's see if you get the right answers. You should make propanamide. Okay, propanamide and HCl gas. Okay, propanamide. Cool, and that's also how you name them, propanamide, N2. Alright, the next one is, next quiz question I've got for you. I'm going to give you the reagents and you have to tell me what products you get. This time we've got carboxylic acid. In fact, we've got a dioic acid there, benzene 1,2-dioic acid. I've used the long name here, dicarboxylic acid, and we're going to react that with PCl5. What will that make? Okay, let's see if you can work out what that's going to make. Pause the video and draw out the product. See if you can name it as well. Products. Okay, you should make 3 products there. You should make 3 products. You should have realised the OH is going to be substituted on the carboxylic acid. We're going to get one acyl chloride group there and another acyl chloride group there. Notice how I've got 2 moles of PCl5. So I'm also going to get 2 moles of HCl gas being produced, vapour, and 2 moles of POCl3. Okay, so the oxygen, remember that's from the O in the OH. So that's benzene 1,2-dioyl chloride. Your product. You should have got that name. Well done if you got that name. Alright. Alright, so the next video is going to be esters. You'll need to have a look at that. Have a look at your esters notes. Get on to page 4 of your notes. This will be the first slide of the video, just giving you a quick intro, and I'm just giving you an example of an ester. So go and find out about that and make sure you can do that next. Okay, alright, so pause this video, you've finished now acyl chlorides, and make sure you've got your notes filled in.